Okay, Eric, can you see my screen?
Yep, I can.
Okay, perfect. We'll just give it a minute it's 11:01, so I think people will probably continue to trickle in, but we'll get started. So good morning, everyone, and welcome to the Invasive Species Center webinar series. My name is Sydney Courier, and I'm the Aquatic Invasive Species Coordinator at the ISC, and I'll be your moderator for today. So before we begin, I'd like to acknowledge that the ISC honors the long history of the First Nations, Inuit and Métis Nation peoples on the lands now known as Canada, and strives to show respect to their ancestors, their communities, and to them individually. We greatly appreciate the significance of the lands, waters, and all living things, and offer our gratitude to the Indigenous people for their care and teachings about our Earth. Our relationships with Indigenous communities are important, and we will continue to listen and learn how we can be in a good relationship with Indigenous peoples, the lands and waters, and all living things, and act accordingly. The ISC respectfully acknowledges that our head office is located on the traditional lands of the Anishinaabe, the Batchewana, and Garden River First Nations, as well as the longtime settlement of the Métis people in the Robinson-Huron Treaty area. The Invasive Species Center is a not-for-profit organization that connects stakeholders, knowledge, and technology to prevent the introduction and spread of invasive species that harm Canada's environment, economy, and society. So we have a lot of great invasive species resources on our website, so I encourage you to check those out. We have species profiles, best management practices, and more. So go take a look at our website. It's www.invasivespeciescenter.ca. You can also sign up on our homepage for our quarterly newsletter, our biweekly media scan, and event invitations, which is where you can hear about upcoming webinars. The ISC has also launched an invasive species training program that offers virtual courses on topics related to invasive species. So we currently have 4 courses available, which focus on different forest invasives, but we'll be releasing some new content regularly, so stay tuned for that. And make sure you check out our website and sign up to receive updates on when these new courses become available. And I just want to do a little plug that from the aquatics perspective, we're working on a marbled crayfish training course right now, so you can look forward to that in the near future. But before we get started with today's webinar, there's a couple things I'd like to mention. So there will be time for questions at the end. So if you have questions at any time, please type them in the question box. I repeat, put them in the question box, not the chat, and I'll read those to our presenter after the webinar. If you're having any technical difficulties at this time, please type that in the chat box or respond to the email found in your registration, and we'll try to resolve that for you. We've also enabled closed captioning, so if you'd like to follow along that way, you can turn that on with the closed caption button on your taskbar. Lastly, there will be a very brief survey following the webinar, so if you could take some time to fill that out, we'd greatly appreciate it. And today's webinar is titled Sampling Effort Required to Detect and Remove Asian Carps During Response Activities in the Laurentian Great Lakes Basin. And I'm pleased to introduce our speaker, Eric Smyth. So Eric Smyth is an aquatic science biologist with Fisheries and Oceans Canada, and he's based in Burlington, Ontario. Eric has a master's degree in integrative biology from the University of Guelph and specializes in population modeling for invasive species, including sea lamprey and Asian carps. Since joining DFO in 2017, Eric has used his skills to evaluate the potential risk of black carp within the Great Lakes, trade-offs of invasive species control programs, and tactics to improve Asian carp detection and removal within the Great Lakes. So thank you so much, Eric, for joining us today. I'm really excited to hear your talk, and I'll pass it over to you now to share your screen.
Perfect. Thank you for having me today. Before I start, just want to make sure one last time that we can all see my presentation.
Looks great.
Perfect. So good morning, everyone. Thank you for coming to my talk today. Today, I want to talk a little bit about the work that myself and Dr. Andrew Drake at DFO has completed to look at sampling effort when it comes down to the response activities for Asian carp in the Great Lakes Basin. Now, before I start talking about the meat and the details of my work, I wanted to provide an opportunity for anyone who's interested in a little bit more information about some of the materials I'm going to be talking about today or the analysis results. All this work is currently published in a public CSAS research document, as shown just right here on the right. The report is available through the public Federal Science Libraries Network search. So by searching through either the title or my name, it should pop up. Same with through a standard Google search. But I've also provided a QR link available just in that bottom right corner. If anyone is interested, you could just use that QR link and that'll send you straight to the report. Now, I know that since this is a fairly broad audience I'm presenting today, that when I mention Asian carps, not everyone may be entirely familiar with those group of species and might be thinking it's actually one type of species. When in fact, when we talk about Asian carp, there are 4 different species that we're referring to. These are grass carp, big head carp, silver carp, and black carp, as shown just right here. These are all non-native invasive species that have been introduced within North America, primarily through the aquaculture industry, either through direct or incidental introduction into the US agricultural fields, and as a consequence through either incidental or accidental release into natural systems. These species have escaped confinement and therefore been successful in reproducing and establishing throughout freshwater systems within the US. Now, as a consequence, they have been starting to expand their range. Black carp in the bottom right being one of the most recent species of the Asian carp to have a successful establishment within US waters. And given their life history and relatively few predators, there's serious concerns about the potential ecological impact that these 4 species could have on the Great Lakes system. Now, with that in mind, what is the current status of these species within the Great Lakes waters? Well, currently only grass carp and bighead carp have been captured within the Great Lakes. It should be noted that although silver carp has not been captured in Great Lakes proper, it has been captured on the Great Lakes side of the cause waterway. So that's the Chicago area waterway system, where some people might be familiar with the electric barrier to restrict Asian carp access into the Great Lakes. So although it's not been found in Great Lakes waters proper yet, it has been found on that the Great Lakes side of that barrier. When it comes down to actual reproduction and establishment within the Great Lakes, right now, grass carp are the only species where reproduction has been detected within the Great Lakes waters. The Maumee River and Sandusky River on the southwestern shore of Lake Erie is where they've been primarily reproducing and where reproduction has been found quite frequently. And more recently, the Huron River, again, nearby to the Sandusky. One very important note, though, is that reproduction has not been detected right now in Canadian waters. And that's pretty much due to a lot of the efforts from numerous agencies, including the DFO Asian Carps Program. So when we talk about the Asian Carps Program, this management program was initially initialized in 2012 when it was looking at the potential effects and risks associated with Asian carp. And following its review in 2017, the project was renewed and is continual operations as part of Fisheries and Oceans Canada. Now, this program has several dedicated components. There are field operations associated with the program, as well as laboratory analysis for captured individuals. There's outreach and education, as well as regulations and support. Now, this program is science-based with management built around 4 pillars that are shown to the right. These pillars include prevention, early warning, response, and management in terms of regulations and pathway management. Now, the spatial focus of this program is to apply these 4 pillars into the Canadian Great Lakes. Now, although government agencies abide by geopolitical borders, fish do not. And so whatever happens on the Canadian water side, we also have to consider what's going on with the American water side as well. And because of that, this program has built really strong collaborations with numerous government agencies, whether other Canadian agencies such as the MNR, as well as various US partner agencies, including USGS, as well as various state departments of natural resources to look at managing and addressing these Asian carp concerns. So for the program itself, there's two key components I want to talk about. The first is going to be about the early detection work. So currently, DFO has a very dedicated early detection surveillance program to assess whether or not various Asian carp species are found in Canadian waters. And the map on the right just shows the various detection sites, surveillance sites that are currently being conducted and surveyed regularly by DFO. Now, the purpose, like I said, is to determine whether or not Asian carp are found in Canadian waters. And these sites are selected based on likely preferred Asian carp habitat. And for these samplings, they are looking at targeting multiple different life stages to maximize a full breadth of effectiveness during their early detection. Now, because they're looking at multiple different life stages, there's multiple gear types that are being deployed for their surveillance. And these include, but aren't limited to, boat electrofishing, hoop nets, mini fight nets, seine nets, trammel nets, trap nets, and finally bongo nets. So there is an early detection program in place, but the question is, what happens when an Asian carp species is detected? Now, whether or not it's detected by DFO or by members of the public or in another agency within Canadian waters, we implement a response program that we have. So following the detection of an Asian carp, strike teams are deployed to search for any other individuals within the vicinity of that detection location. Now, typically during these responses, boat electrofishing is used, which is shown just in the picture on the right, along typically with trammel nets. And there is an emphasis to target more carp habitat, but it's not exclusively targeting carp habitat during these responses. Now, we do have a little bit of a record when it comes down to responses in Great Lakes. So since 2015, there's been 10 responses in the Canadian waters of the Great Lakes proper following the capture of an Asian carp. And of these 10 responses, we've had 12 captures. So these captures have all been grass carp. In 2015, we had one carp captured in Tommy Thompson and two in the Toronto Islands Marina. You may recall, now it's been about 10 years ago, but there was a fairly large media blitz of the consequences of these carp being captured in Toronto, and really made a lot of different news outlets, and a lot of people started to wake up regarding the concerns regarding grass carp within the Great Lakes. In 2016, we had another large event where 9 carp were captured within Lake Gibson. And since then, we haven't had any carp that were captured during a response within the Great Lakes proper. Now, when it comes down to the response itself, people ask, well, what's the magnitude of these searches and responses? Well, the magnitude response in terms of both the number of strike teams that are deployed as well as their corresponding search effort really depends on several factors. These include species, ploidy, so whether they're the sterile triploid fish or a fertile diploid fish, as well as the life stage that's detected. Now, when it comes down to the magnitude of responses and what this means, it means that the magnitude of response may differ if a sterile triploid grass carp is detected rather than a, let's say, diploid bighead carp. We'll see a vastly different response magnitude in those two situations. On the same side, if we see and detect a adult grass carp versus a young of year juvenile grass carp, which could suggest that reproduction may be occurring within Canadian waters, that would have a different response, a magnitude response as well. Now, the key thing, though, with these response efforts is that when it comes down to implementing these responses, there are decision trees that are placed by managers to understand what type of magnitude should be recommended based on these different factors. But when the response should end is much more based on professional judgment in the field, where field crew leads are basically assessing, based on the reason for their response, the type of effort they've currently conducted, what does the response area look like in terms of structure, what have they been catching or not catching. These are all factors that are basically put together to determine when the response should sufficiently end and strike teams could be called back. Now, with this in mind, there was a real key question that was posed to us at DFO Science, was determining, well, how much effort should really these strike teams be considering and implementing during a response? And is there any way we can provide some sort of defensible response instead of moving or relying on professional judgment? Now, as you can see, this is a challenging question to ask. We don't have a lot of responses, and we don't have a lot of catch successes from these responses. So how do we start answering this question? And to do that, we rely on simulation modeling. Modeling is a great tool that allows us to look at all kinds of various scenarios and really pick apart these scenarios to understand what makes them tick and what we can get for outputs from that. So for our simulation models, we developed a hypothetical response area where Asian carp would occur and that strike teams would deploy. We considered a response area that was fixed at around 750,000 meters squared that was composed of small 5 by 5 meter cells. So the reason why we chose the 750,000 square meters or 75 hectare wide area is we talked to the response crews and basically said, what is the likely size of a response area you guys would respond to? And so we threw a bunch of numbers, and 75 hectares seemed to be a realistic, reasonable area that they would respond to. So within this hypothetical response area, we had various fish that we would assign to different habitat cells throughout the response area. And these fish were assigned to a cell, one of these 5 meter by 5 meter cells, and were assumed to remain in the same cell during the entire response. Following that, strike teams would then sample the response area systematically looking for carp. And within this simulation model, we had several core uncertainties and therefore corresponding assumptions associated with this model. The first uncertainty was, what was the probability that fish would be caught following a sampling event in an occupied habitat cell? So basically what this comes down to is you have a cell where fish are, crews are going to be sampling over that site, and what is the probability that the fish in that sample site is being caught from a single sampling event? We define that uncertainty as the probability of capture. And in our models, we examined a range of probability of capture values, ranging all the way from 0.05 to 1. The reason why we didn't use the value 0 is basically crews would be infinitely searching response areas with no success of ever capturing that carp if a probability of capture value was 0. The other uncertainty was, what is the probability that fish could co-occur within a habitat cell with other fish? This uncertainty was what we defined as aggregation, and we'll be talking about it throughout the presentation. And so we examined various aggregation rates, values ranging from 0 all the way to 1. So the 0 being no aggregation, that fish are occupying their own separate cell, to 1 as they're all occupying a single cell together. So let's talk a little bit about the base model and how this model was constructed and operates. So first, we have our fish. We talk about the fish assignment within our response area. So this grid that you see right here represents our response area. And in this scenario, we're going to be dealing with looking at 5 fish within our response area. So first, we deal with fish assignment. The first fish at the top gets randomly assigned anywhere within the response area. Then for the second fish, we determine whether or not this is an aggregating fish or not. And in this case, we'll say this fish was determined not to be an aggregating fish based on the probability of aggregation that we were using. The next fish, we say, okay, fish 3, is it aggregating or not? This one is. Okay, so it has to randomly be sent to one of the 2 previously occupied sites. In this case, the fish is moving to the cell in the top left. Next is fish number 4. This fish is seen to be not aggregating, so moves to an unoccupied site. And we lastly have fish number 5. This one's deemed to be aggregating. It goes to an occupied site and is found to be going to this middle one. So what fish aggregation actually looks like across our various scenarios of a response area across the aggregation rates is something similar to this, where we have various grids representing a response area. I'll use my cursor to highlight this. So in an aggregation rate of when it's 0, we can see that in the case of 10 fish, we have 10 cells that are colored light blue, representing a low density of fish at 10 various sites throughout the response area. As we increase aggregation rates from 0.25 to 0.5 to 0.7, what you're seeing is fewer number of sites that have blue colors representing fewer sites where fish are occurring, and darker colors representing greater densities of where fish are occurred amongst those occupied sites. To finally, when we end with an aggregation rate of 1, where we have all 10 fish in a singular 5 by 5 meter cell within that response area. So that was fish assignment in relation to fish aggregation. Our next step is actually looking at what the model does when we have fish throughout the area. So what the model is doing is basically considering this, our electrofishing crew right here in the bottom left, that'll be moving systematically from left to right throughout the response area, sampling every habitat cell it comes across. Once it comes across an area where fish are occupied, fish are captured or either left based on the probability of capture that we have assigned in that model simulation. So if it's less than 1, there'll be some scenarios where fish are captured and removed from the system. In other cases where it passes over fish may not actually be captured and will have to necessitate further sampling down the line. Now, what we're recording in this model is several things. First is we're looking at effort in the terms of number of sites are sampled and subsequently number of passes are needed to be occurring for crews. And we're looking at the amount of effort in terms of sites and passes for detection, which represents the amount of effort for the very first fish to be captured and removed from the site, as well as local removal when all fish are effectively captured and removed from the site. So in this scenario, how we've ended in the top right cell, we still have 3 fish that are occurring in the response area. What our model would do is repeat sampling again from the bottom left and continuing in the systematic sampling pathway and method until all fish are successfully removed from our theoretical response area. So with that, let's start looking at results. What I have right here is the results for the amount of effort required for a successful detection of Asian carp within a response area. My y-axis right here is representing the mean relative effort that's required for detection. On our x-axis is the probability of capture, ranging from 0.05 all the way to 1. We have various color lines, shown right here, which represents various abundances of fish, where red is representing 1 single fish in the response area. And as we increase abundances from 1 to 25, we move from a red color to cooler colors to finally this purple magenta color right here. Now, these results are based on an aggregation rate of 0.05, and we'll be talking about that implication of those that rate fairly shortly. But first, I want to talk about the results right here. As you can see, we're having a nonlinear result or trends observed by looking at detection, a nonlinear in 2 aspects. First is nonlinear in the relationship for probability of capture, where a low probability of capture results in a large amount of effort that's required for detection. In the case of a single fish, we are going to need to sample approximately 17 full passes of the response area to detect a single carp when 1 carp is present. But small increases in the probability of capture at a low probability of capture rate make substantial differences, all the way to about probability capture values are close to about 0.5. Once you're there, very small increases in probability of capture rates have little effect on the mean relative effort in the end. So there's one nonlinear relationship. The second nonlinear relationship is a relationship on effort in terms of abundances. As you can see, the change in effort that's required for detection is a substantial change when we move from a single fish, this red line right here, to this yellowy orange color right here, which is representing 3 fish. So large magnitude of change that's seen in the way of number of passes required for detection. But as we increase the abundances of fish within our system, we start to see that the impact on detection is vastly smaller. So changing from 20 fish to 25 fish in this purple magenta at the bottom, so you can see adding 5 fish has little effect on the mean relative effort. Now, I mentioned that this is all for results when aggregation is fixed at 0.5. So we wanted to look at varying aggregation rates on how this could affect mean relative effort. So what we did is we took a scenario where we had 25 fish. We produced a very similar plot as before, where the y-axis represents mean relative effort, x-axis means probability of capture ranging from 0.05 all the way to 1. The color lines now represent aggregation rates, where red is 0, and increasing aggregation rates move from red to cooler colors to finally this purple magenta color, as you can see right here. And when population abundances are at 25, we can see that purple line. As we move an increased probability of capture, it doesn't really have a large effect on the mean relative effort that's required once we get to a value of about 0.1, 0.15, and then it fairly stabilizes throughout various probability of capture rates. And also, too, one thing to notice is that it seems to be have a fairly large relative effect compared to when aggregation rates are 0.75 or lower. We're seeing much lower relative effort. Now, although this does appear to be a fairly substantial effect, we do have to recognize the scale that we're looking at right here. That despite having a large aggregation rate and having a greater effect on effort, this all requires less than a single pass of the response area for detection. So large relative effort, but relatively very small absolute effort change. Now, these results are great, but it's really hard to communicate these results to field crews and figure out exactly where they are, and then they have to recognize what the potential abundance is in the system, which for crews, they won't have that information when they go to a site. So what we did is we took these results, and instead of just talking about effort for detection, what we changed is our axes to understand what type of abundance would occur depending on the number of empty passes that crews would experience. Because what we're finding based on a lot of the sampling responses is crews are expending a vast amount of effort for a lot of their responses are getting no fish, no Asian carp captures in their sampling. So there's a large amount of resulting in empty passes for when they conduct their searches along a response area. So what we did is we created these figures. Each figure right here in these panels represents the results for an abundance of a set number of fish, ranging from 1 fish to 25 fish. And what we have is the probabilities right here, which is the y-axis, for representing the probability that a population of this number of fish exists in our response system. So probability for 1 fish, 3 fish, 5 fish, all the way to 25. And our x-axis represents the number of empty passes experienced by crews during their response. The color lines are representing the probability of capture rates ranging from 0.05 all the way to 1. Where again, red is representing a low probability of capture of 0.05. And as we increase the probability of capture rates, we're moving from red to cool colors to finally these magenta colors at rates of 0.95 and 1. Now, how to interpret this for field crews is field crews can look at this example right here where we have 25 fish. And they can say, looking at the x-axis and say, well, we've experienced four empty passes, no fish have been captured. What's the probability that 25 fish exist in our response area? Well, based on these lines, we can say that there is a near zero probability that 25 fish are found in that area, even when probability of capture is incredibly low at that 0.05, and saying that once you hit 4 and there's been no successful fish, then it's extremely unlikely that you're having 25 fish in your system. On the flip side, we can look at this scenario right here where we have 1 fish in the system, and we ask crews and they say, well, we've experienced 5 passes, complete passes, no fish whatsoever. What's the probability that 1 fish could remain in the system? Well, what we can look at is say, at very low probability of captures, that red line right here, even though you've had 5 passes with no successful Asian carp captures, you're still approaching about a 75% percentage or a 0.75 probability that 1 fish remains in your response area. So this is all the results that we presented for the detection. But one thing I want to also highlight is this is just one side of the response. Detection is valuable, but we're also really focusing on local removal. So what does effort look like for that? So right here, we have a similar figure to what I presented before. We're looking at mean relative effort and then the way of number of passes of the response area for local removal as our y-axis. Our x-axis is probability of capture ranging from 0.05 all the way to 1. Our different color lines are representing the abundance of fish in our response area from 1 to 25. And in this scenario, our aggregation rate is fixed at 0.5. So a few things I want, I'm sure everyone's noticing right off the bat. Number one is that the colors are effectively flipped from what it was for detection. For detection, the highest amount of effort was required when abundance was for one fish. Here, the highest relative effort required is when abundances are 25, which makes sense. More fish will require more effort. But I want to point out what the mean relative effort is going to be required under that worst case scenario. In that scenario, we're looking at approximately 70 passes of the response area would be required for complete local removal of 25 fish, but that only occurs when probability of capture is incredibly low. And this leads me to the second point I want to highlight. Similar to this, the detection results, we're seeing multiple nonlinear relationships here. So for local removal, small changes in the probability of capture at low probability of capture rates make substantial differences. But as we move closer to that 0.5 value for probability of capture, increases in probability of capture at this point or beyond have little to no influence on the effort that's required for response for detection. The same is to be said on abundances. As you can see, changes from 25 to 20 to 15 individuals has some, I would say, relatively minor effect on the mean relative effort required for local removal, versus small changes from 3 individuals to 1 individuals have a much greater influence of effect on the effort required for local removal. So we're seeing nonlinear relationships again across the probability of capture and the abundances that we are examining. Now, these results are for when aggregation rates are fixed at 0.5. So we wanted to look at the aggregation rates and see if it had any effect. Excuse me. So right here is the results for a scenario when we have local removal with varying aggregation rates. Same graph structure as before, where we have mean relative effort, probability of capture is our x-axis. We have aggregation rates reflected as these different color lines, where red representing 0 and this purple magenta representing aggregation rate of 1. And as you can see, there's almost no influence of aggregation rate on the mean relative effort for local removal when abundance is 25. We do see a very small difference when probability of capture is at 1, but overall almost no influence whatsoever to be said from aggregation rates. So similar to the detection work, providing these graphs to field crews is not the most intuitive manner to provide with them. And instead, they're probably going to be asking similar to the detection work, well, we've done so many passes, what can you tell us on our success rate? And so what we've constructed is similar figures to the previous one, where we have each panel representing the output for a fixed population of 1 fish, 3 fish, 5 fish, all the way to 25 fish. Our y-axis represents the probability of local removal within that response area, and x-axis represents the number of passes conducted. Each line coloration is reflected based on the probability of capture, where again, red is 0.05. And as we increase probability of capture, we are moving to cooler colors to finally where this dark purple magenta color is at 1. Now, how we interpret these results is that we can talk to crews, and if they say, well, listen, we've got 4 fish or 4 passes that we've completed, let's look at the 25 fish scenario. What is the probability that we have successfully removed 25 fish? And what we could say is, well, at 4 passes, we look up here, and it basically, if you have a probability capture of 0.8 or higher, you have an almost near 100% probability value of 1 that 25 fish have been, your 25 fish have been all locally removed from your system. Versus if you say, okay, we've done 5 passes, what is the probability that there's been complete local removal for 1 fish in the system? Well, if your probability of capture is fairly low at 0.05, you only have about a 0.25 probability or 25% chance that your entire system has experienced local removal when population is low at that 1 fish. So we provided these results in a much more intuitive way for crews to kind of identify, where they can look at across ranges of their probability of captures, what they think they are successfully at, at various scenarios of sizes and say population sizes and say what type of level of comfort they could be at for the response area. And this type of results would also be highly valuable for managers when setting guidelines of saying, okay, we want crews to have a confidence level of 0.7 or 0.8 that they've successfully locally removed this any Asian carp from the area. What type of efforts required to do that? Now, all these results have been provided based on a base model that's been fairly simple, straightforward, and doesn't have a lot of unique elements to it. And what we found after we constructed the base model is that there's numerous other uncertainties and scenarios that we should start considering and exploring. Some of these scenarios and questions that were asked was, first one is, how is effort affected by sampling method? So whether we're doing a sequential kind of one by one sampling method as shown before versus a more randomized site selection process. Another one is, how is effort affected by crew knowledge of preferred Asian carp habitats, so such as a much more informed sampling approach? How is effort affected by improving sampling tactics, such as a repeat sampling design for sites where fish have been captured and detected? And lastly, how is effort affected by fish movement to avoid sampling crews? So to understand how each one of these different scenarios and corresponding models differ from the base model, I provided this table to kind of highlight that, where each purple cell represents a differing change from our base model. So our base model is shown right here on the left, where we had our response area and sampling area representing in our theoretical space of 75 hectares. We have probability of capture rates ranging from 0.05 to 1, fish aggregation rates ranging from 0 to 1, with a systematic sampling response, with one site being sampled per pass and with no fish movement. When we moved to the randomized sampling model, everything kept the same except for the response sampling, which was which was designed to be in the randomized approach rather than the systematic approach. In the informed sampling model, here we've changed our sampling area. So instead of fixing at 75 hectares, we looked at having and quartering that response area, sampling area to look at different varies of buffers around what is considered to be a highly suitable carp habitat. So if we had a very wide buffer or very narrow buffer, and I'll be talking about this a little bit later. We also had response sampling was a little bit more variable than the base model, where it was still systematic, but it was more systematic towards the informed habitat sampling area. For the repeat sampling model, everything was kept the same, except that once fish were captured within a 5 by 5 meter cell, there was subsequent resampling at that particular cell. So it's either done once, 3 times, 4 times, or 5 times. And lastly, for fish movement model, everything was kept the same, but we had a movement probability where when crews approached a cell or site where fish are occupied, what was the probability that fish would leave that site and move to another site away from the field crews? So how does this look? So I've got a quick animation again. Our base model, we have the systematic approach. Crews are moving from left to right. They pass over occupied habitat cells where fish are occupying, where they could be captured, depending on that probability of capture rate we've used. Versus when we looked at the randomized sampling approach, what we see instead of moving from left to right, crews are moving now randomly throughout the site, sampling sites at random, some cases where they actually hit occupied sites, and other cases where they're missing the carp completely. Next is the informed sampling. So this one was a little bit more complex because what you can see here is we took the existing response area and designated a subset of that area to be the highly preferred carp habitat. So when it came down to fish assignment, we would only assign fish to the preferred habitat, which is symbolized right here in this kind of purple shaded cells. Now, as I mentioned, we considered different buffers when it came down to sampling, and it reflects on how well informed the crews are. Whereas a very large buffer is similar to the base model, where crews are sampling the entire response area, regardless if it's in the preferred habitat or not, to something that's much more well refined and well informed, where there's a very small buffer and crews are sampling just well within that highly preferred habitat. is shown right here. Again, both of them are in the systematic manner. It's just how much of that entire response area are they actually sampling. Next is the repeating sampling model, where again, crews are moving systematically from left to right. However, in cases where they successfully capture a fish, they remain at that site and conduct repeat sampling several times, and then carry on throughout the rest of the entire response area. Now, this is really kind of targeted towards the approach of where fish could be aggregating within cells, and therefore the greater level of aggregation, we would expect the better value the repeat model would have. And lastly, we have the fish movement scenario. Again, same type of structure to all the other models, as we have crews moving left to right. But as crews approach an occupied habitat, there is a probability that those fish within those sites will be moving to other sites away from the field crew. Now, if they do, they can still be susceptible for capture, but it depends on where they're moving, whether or not it's farther down within the pathway of the electrofishing crew or prior to that. We left that completely randomized when it came down to fish movement. So with all these models, we did the same type of outputs as our base model, where we're looking at effort for both detection, which is again the capture of your very first carp, as well as complete local removal. And we wanted to compare these against the base model. So by doing that, we can understand what would be the potential effect when it comes down to effort required. And when we do these comparisons, looking at this level of effect is what us modelers like to refer to as the sensitivity of these different various model scenarios and model structures. Now, with this in mind, though, we had a little bit of a challenge, because if you recall from our base model results, we had a lot of nonlinear effects on what would happen when you're looking at across abundances or across probability of capture values. And so for our sensitivity analysis, we wanted to look at detection and local removal across various abundances and probability of capture rates. So we decided to look at a range. We thought what would be a realistic and reasonable range to consider. So for abundances, we looked at between 3 and 25 fish. And based on literature estimates we could find for probability of capture values, we used a range of 0.05 to 0.7. And with that, we did various combinations to create these 4 different conditions that we were going to explore using our sensitivity analysis. The first is the low abundance and probability of capture, where we looked at 3 fish and when probability of capture is 0.05. Second one is low abundance and high probability of capture with 3 fish and probability is 0.07. Third one's high abundance and low probability of capture with 25 fish and probability is 0.05. And the last one is high abundance and probability of capture with 25 fish and probability is 0.7. So let's look at the sensitivity results when we consider for detection. This is our base models when we considered was when aggregation was fixed at 0.5. And what we have is the 2 top panels are scenarios where we have abundances of 3, and we're looking at different capture rates of 0.5 and 0.7. The bottom panels are when we look at abundances of 25 and probability capture rates of 0.05 and 0.7. So to think about this another way, columns represent differing in probability of capture rates, so 0.05 and 0.05, and 0.7, versus rows represent different abundances, so abundances of 3 and abundances of 25. And what we have here as our x-axis is the different scenarios that we were looking at for their sensitivity. So looking at varying aggregation rates, the influence of random sampling, repeat sampling, movement or avoidance, as well as inform the idea of that large buffer where we sample everything regardless of fish habitat preference, or a smaller buffer when we are actually sampling the preferred habitat by fish. The y-axis represents the change in effort for detection when compared against the base model. Now, a few things you might see by looking across these figures is that consistently, looking at the small buffer scenario, we found consistent declines in the amount of effort that was required for detection, regardless of abundance or probability of capture rates, which is great. But we also found some other interesting outcomes as well. For example, the large buffer scenario really only had an impact when we saw the probability of capture increased when dealing with abundances at 3. So you can see when probability of capture rate is low at 0.5 has little to no effect on effort, but a much higher relative change in effort when probability of capture is 0.7. Another one we can see is when looking at abundances of 25, we can find the influence of aggregation had a little to no relative effect on effort when probability of capture was 0.05, but a much higher probability of change in relative effort when probability of capture was 0.7. So we had this for our results for detection. We also did a similar analysis when it came down to local removal. Same structure as before, where we have our columns representing the same probability of captures of 0.05 to 0.7, rows representing abundances of 3 and 25, our various scenarios, and the relative change in effort when compared to the base model. Here, what we found the same with detection is that for local removal, implementing that small informed buffer had a consistent and relatively large influence on decreasing effort required for local removal. But similar to the detection results, we found that certain scenarios had greater influences depending on the abundance or the probability of capture. So in the cases of random sampling and repeat sampling, had very little relative effect on when abundances were 3 and a low probability of capture. But when we increase that probability of capture to 0.7 on the right, as you can see, the influence of these scenarios increase quite substantially. We also can see something very similar when we're looking at the abundance of 25 scenarios. So again, probability of capture of 0.05, little effect. When we increase the probability of capture to 0.7, a much greater relative effect on local removal. So in summary, I want to highlight again that DFO has a response program where targeted sampling occurs in locations where Asian carp are detected. Effort required by crews to detect and remove all Asian carp present within a response area was identified as a key uncertainty. And multiple passes would be required for detection and local removal, particularly when probability of capture is low. So when we looked at effort required for carp detection, that ranged from 0.07 to just shy of 14 passes of the response area across our abundances that we explored and across probability of capture rates ranging from around that 0.05 to 0.7 rate, which I mentioned in our sensitivity analysis, is probably a little bit more of the likely probability of capture range that we could experience in the field. So still, 14 passes under the worst case scenario is a lot of effort required for detection. What's even a little bit more depressing is that for local removal, that range of effort that's required could be 0.72 all the way to just shy of 70 passes across a response area. But this is across abundances of 0 to 25 fish, with that probability of capture ranges going from 0.05 to 0.7. When it came to our sensitivity analysis, we found that sampling with a smaller buffer, that targeted sampling approach, consistently decreased effort for detection and local removal. And that random sampling and repeat sampling had a greater influence on effort for local removal when probability of capture was high. So with this in mind, the big question is, what's next? Well, as you can understand from our analysis, the probability of capture is a key influence on effort required for both detection and local removal, particularly at low probability of capture values. So again, remembering when we have our figure right here for the effort required for local removal, small probability of capture rates mean a large number of effort, or a large amount of effort is going to be required for both removal and detection. But just able to be successfully increasing probability of capture at those low rates can have some substantial effects and improvements on the amount of effort that's actually required. When we looked at the literature, current estimates of probability of capture are likely to range, as I say in our sensitivity analysis, somewhere between 0.05 and 7. Now, there is some recent work conducted in the Great Lakes where a marker capture study was done to simulate what the responses are from DFO, DFO crews, and a way to understand what the potential probability of capture rate and success is of these crews. Based on those analyses, we have found that the probability of capture could be as low as 0.05. Now, one very important thing to recognize with a lot of these literature estimates as well is mark recapture study is these probability of capture rates are based on primarily surrogate species, primarily common carp. So a question remains as how accurate is the common carp probability of capture rate for our various Asian carp species? And right now, that's something that we don't fully understand or know. So with that in mind, is our effort should be focused on the search for better capture rates? Well, that's a challenging situation to be placed in. And the reason is that probability of capture can be affected by many external factors that can vary. When we're dealing with a highly visual style sampling method, such as electrofishing, probability of capture is going to be dependent on many factors, primarily on the ability of crews to be able to see the fish in order to net them. So habitat conditions such as vegetation or turbidity that are expected to vary could affect the success of probability of capture. If you're sampling in a highly vegetated or very highly turbid area, you're unlikely to see any fish within that particular site, and so your probability of capture is likely to be quite low. This is also even further compounded and challenging as probability of capture is unlikely to be consistent across a response area. If you have areas that are both highly vegetated and then deeper and less vegetated, more easily visually seen for response crews to see fish within those sites, we would expect probability of capture even within a response area to vary. And it's a little bit harder when you start dealing with that, trying to figure out how do we improve probability of capture rates across these sites. So one thing we have to recognize is look back to our sensitivity analysis. And our results did demonstrate that informed sampling alone could substantially reduce effort. So if probability of capture is low, we should target preferred habitat, because if you recall, that small buffer informed sampling design substantially decreased the amount of effort that was required for both detection and removal. And therefore, moving to focus on improving habitat associations and the understanding of those associations with Asian carp presence could minimize the response effort that's required, despite the presence of a low probability of capture experienced by crews. And with that, I'd like to thank everyone for their time today, and I would be happy to field any questions that anyone may have at this time.
Thank you so much, Eric. I can appreciate how much work went into all of that research. That's incredible. Folks, if you have a question, put it in the Q&A feature, and I can read those out to Eric. In the meantime, I have a couple questions. Okay, so your analysis examined the probability of capture for electrofishing alone, but strike teams have also used trammel nets in conjunction with the electrofishing. So could your analysis incorporate trammel nets? And if so, how do you think that would influence your results?
Oh, that's really interesting to think about, because that's a common question people have is, okay, we change sampling gear type, how does that affect our results at all? And what we've tried to do with this modeling design is keep it as versatile and simplistic that it does adjust fairly easily to other active sampling approaches. So in the case of adding trammel nets, what we can suspect is that by allowing trammel nets within the system, you're likely to be increasing your the herding ability to capture fish and isolate them and improve effectiveness of electrofishing. And so the simple answer to that is if we take these results, if you add elements such as trammel netting or changes to your amperage or other design, you could actually be moving from somewhere here that is quite low if deemed based on field results, you could actually be inadvertently increasing your probability of capture to the right. And so the way to think about this is, as I mentioned, literature estimates right now peg us to be somewhere in this range. And we might be able to find with additional testing and exploration that when you add something like trammel netting or changing your amperage, what you're actually doing instead of ranging from 0.05 to 0.7, we might be moving somewhere closer to the 0.25 to 0.5. So the value of these models is that they're incredibly open and versatile that allows for these type of relatively fine-tuned adjustments by the sampling crews without having to rerun the entire analysis.
Okay, amazing. I see a question from John in the chat. Did you think about modeling different capture probabilities for adults versus juveniles?
Directly, no, we didn't. But the way to handle that is, again, if you separated your fish population of how many adults and how many juveniles could be in the system, you would be able to use with this exact same model right here. We can expect that maybe our probability of capture could be lower for juveniles, and we may expect 5 juvenile individuals to be in the system. Here's the amount of effort that would be required for local removal based on the probability of capture of juvenile individuals and their numbers, versus let's say the 1 or 2 or 3 adults that are present in the system, and we think there are much higher probability of capture for them. We would follow again on our x-axis where we think our probability of capture is for adults, and then line that with the likely number of adult individuals that could be there, and therefore what is the corresponding mean relative effort required for that. Right now, when it comes down to the estimates that are available for probabilities of capture for electrofishing, we don't have that resolution to separate or get a understanding of how vastly different this would vary for even our surrogate species. So it's hard to really kind of narrow that range for these Asian carp species that we examine.
Okay, thank you for that fulsome answer. You see, someone's complimenting you on a great talk, Eric. And I have one more question. So your analysis explored the effect of the highly targeted sampling within grass carp habitat during response. And how close are we to pinpointing where grass carp may occur within a response area with high accuracy?
That's the $1 million question right now. It's really hard to look at habitat associations when you're dealing with rare species, and rare in the sense of either imperiled species or invasive species early on in their invasion. Right now, there's been substantial effort that's been placed by our American partners, where they're sampling in the Maumee and the Sandusky areas to look at what type of habitat associations they can look for to maximize their effectiveness while effectively trying to fish out all Asian and specifically grass carp within their systems. Right now, there has been some associations that have been found to hold some truth. So looking at large woody debris in the river, as well as heavily macrophyte areas, seem to be really great for grass carp. But it's still something that's a challenge that people are facing. And we're finding every year something new that's interesting. So whether or not shallow areas are been successful, or more deep pools that act as refuges could be more successful for capturing more carp. But at this stage, we're still very much learning while doing for this invasive species, which makes it very challenging and exciting at the same time, because we're always finding something new that we never thought about when it came down to managing Asian carp.
Okay, very interesting. I see one more question. This is more broadly related to just the Asian carp program and like the name. So referring to Asian carps as Asian carps. So Anna says, I've been looking into the idea to change common names for aquatic invasive species for more inclusive names. Regarding what you call Asian carps, we started to use the appellation invasive carp. Do you know if the appellation is called to change for the Asian carp program? Obviously, because there's concerns with negative connotations referring to the carps as Asian carps. So I don't know if you want to speak to that at all from a DFO perspective, but I know for the Asian carp program, like from the ISC perspective, we're working with our partners to come up with a more inclusive name. And so that is a process. And I don't have like an exact timeline, but that is a priority.
Yeah, to my understanding, DFO is in kind of a very similar approach, where the concerns of, I will say, the problematic connotation around the term Asian carp has been identified and recognized. There has been a process in place to look for an appropriate alternative title that would description that is much more inclusive. The exact timeline when it comes down to when that will be implemented and what exactly that the choice of what that new term is, I'm not privy to at this point, but I do know that that is something that's currently underway right now at DFO.
Perfect. Thank you. Okay. If there aren't any last second questions for Eric, oh, Anna says, great, thank you for the answer. Thanks, Anna, for your question. I don't see any other ones coming in, so I think I'll take over the share screen now and just do a couple closing slides. Thank you, everyone, for your questions. Okay, thank you again to Eric for presenting today, and thanks to all of you for tuning in. This webinar was recorded and it'll be posted on our website and our YouTube channel. So just a reminder to please take a couple minutes if you can to fill out our survey. We would greatly appreciate it. And our next webinar will be on October 16th at 1 p.m. and it is on invasive species action through community science. So stay tuned for that. It's going to highlight ISC's hemlock woolly adelgid monitoring network, our beech leaf disease monitoring network, and our emerald ash borer and black ash community action project. And the presentation will be done by 3 of our ISC staff. So this concludes today's webinar. If you are looking for any more resources on Asian carp or invasive carps, I direct you to asiancarp.ca. There's lots on there, including like how to ID and report. And then I don't know if people have questions for you, Eric, can they reach out, or where would you like to direct them to?
Absolutely. So my email address is eric.smyth@dfo-mpo.gc.ca. I think that the contact information, again, if you go to the URL, I think on the report might have some of my contact information there. But yes, feel free for anyone who's curious about some of the modeling work or what are kind of our next projects we're working on to support Asian carp. We more than gladly talk about that. If there's something that people are interested about responses and the current work that's being done in the field, I can easily direct you to the more appropriate party. Will have more information on that than I would.
Okay, awesome. Thank you so much again, Eric, for your time. That was a great presentation. I know I learned a lot. I'm sure everyone's brains are just blown by all of that. Thank you again, everyone, for tuning in. I hope everyone has a great day. Okay, lots of thank you, Eric. Nice presentation. Perfect. Okay, well, I can close the video now if you have any like closing questions for me.
No, not yet. I do notice that there was I think a modification on the question that someone was asking when they said the name change, they were saying like big head, silver, black, grass carp names. So I don't know if that was the same person that had asked that question or not.
That's a different person.
Okay.
But I think they were just saying like about all of them, right?
Yeah.
I think that's essentially.
Which I know that has always been a very contentious topic for a lot of people. But yeah, I have no understanding of any sort of change for those common names. But yes, the term Asian carp, since we have yet to officially announce a change, we are still going ahead with referring to them as Asian carp and referring to the Asian carp program at this time. So
Yeah, that was my understanding as well. So that's good. Now everyone's on the same page.
Yeah, and it's a challenge. I get that because for every suggested alternative, you have people who will come in and say, I don't know if I agree with that, or well, this isn't clear. So it is a very for such a substantial change of a name of group of species as well as a program at DFO, we want to make sure we do it right. So yeah.
Absolutely. Yeah. Not something to just rush.
No. Okay, so that's it for me. Do you have any questions yourself or any, concerns about sharing materials with that? I have no problems with making sure everything is shared online. Like I said, there's the QR code I tested even today to make sure it links directly to the report. So we have that.
Yeah, I think so. Maybe if you could just send me can you send me the QR code in an email? Because I'm just wondering if I could link that in like the YouTube notes, maybe,
Sure.
so that people could access it.
Yep, I can take that care of that very shortly.
Okay. M says she already has the link. Okay.
Oh, perfect.
Okay, so we're all good then.
Wonderful.
So, and yes, someone's asking, will there be a link of the recording? The recording will be on our website and also on our YouTube channel shortly. But okay, thank you so much, Eric. I hope you have a great day. And yeah, it was a pleasure listening to your talk today.
Well, thank you. I love the opportunity of talking about a lot of really interesting, exciting work. As I mentioned earlier, when you mention modeling, not a lot of people get very excited about that. It's just seeing a lot of numbers and a lot of figures, but we try our best to make sure it's digestible for everybody. And it's important messaging, I think, out there. It's talking to Dave Marson and the crews, the number of passes that people might have to implement for responses. It's not an answer that we want to hear, but it's an answer that we need to hear. And so, it's really helpful for guiding, crews to make sure they're doing the best job they can out there, and where effort needs to be placed on by crews and DFO sides to make sure we're as effective as we can be out in the fields.
Absolutely.
Yeah.
Yeah.
Okay.
Yeah.
Well, again, thank you for organizing this, and it was a pleasure trying to talk and set this up. So thank you so much, and all the best. And I'll look forward to hearing the next webinar that comes around, because I've attended, I think this is my 5th time, although being a presenter, but yeah, I tend to attend a lot of the webinars. They're great stuff, so I'm happy to contribute to it.
Okay, that's awesome. I'm so glad to hear that. That's great.
Yeah.
Okay, well, thank you again and take care.
You too. Bye.
Bye.